Okay, welcome to note set M03, our third on MATLAB. And in this one we're going to talk about vectors and matrices, how we make them, how we make a vector, how we can make a matrix, and then talk about arithmetic, but from a linear algebra point of view. In the next set of notes, or, well, I don't know if it'll be I guess it'll be the next one. We'll talk about some other kinds of arithmetic to do with vectors and matrices that are not linear algebra oriented, but are useful for other math things. All right, so the important thing is, well, you've already learned that MATLAB stands for Matrix Laboratory, so it's no surprise to find that MATLAB is all about matrices. It's matrix oriented. So MATLAB just thinks of all of its variables as a multi-dimensional array. So even when you're just defining a variable that has a single numerical value, it's still really thinking of that as a special case of a multi-dimensional array. It just happens to be a 1 by 1. And that makes it different than many other programming languages. So you may have learned C or C++ or something like that. Those languages, in particular C, are not matrix oriented or array oriented. And so when you want to add things together, you can only add element to element. So yes, you can define arrays in C, but to operate on them, you have to write loops to operate on them element at a time. Whereas MATLAB, you can just say, add this matrix to that matrix, and if the sizes are correct, it'll just do it. So let's talk a little bit about this. Here's how we would create a vector. One way, there's many ways that we can do this, and MATLAB is a very powerful language, so there's lots of different ways to do things. But here's a simple thing. It uses this colon command, which is very powerful. We'll see in the next slide or two other ways to use this, but we can simply say a starting number, an ending number, and if we just use the colon, it's going to jump by increments of 1. So this will actually start at the number 1 and go up to the number 10 in increments of 1. And so if we want to see what we created here, you can see that we put the semicolon at the end so nothing spews out when we make that command. But what's been stored in the variable x? Well, it's now an array. In this case, it's a row vector. And since we said start at 1, go to 10 in increments of 1, it starts at 1 and goes all the way out to 10 in increments of 1. You can see that we're incrementing by 1. And so you can see that this is a row vector, so it's 1 by 10. Because of the way that it was created. So just a little more detail on creating row vectors using the colon. So the colon operator has a general command, start, step, end, and you have two different colons in there. So here we start at 1, we stop at 10, and we have increments of 2. So notice in this case, we actually don't get the last value. We get the starting value, but because we are jumping up by 2, we go 1, 3, 5, 7, 9. Now the next jump by 2 would take us to 11, which is beyond the stop or the end. And so we don't get that one because it can't give us something beyond the ending value. And as we just said, if we omit the step in the middle, we have a default step size of 1, as we saw in the previous. And there's no need to limit things to integer values. So we start here at 1.2, our step size is 0.2, and our end point is 2.4. And so we start at 1.2. Our step size we can see here goes by 0.2 each step. And in this case, since stepping by 0.2, starting at 1.2, hits 2.4 along the way, which is our end point, we will actually have 2.4. But suppose I put 2.5 here, we would get exactly the same result that we have with 2.4 there. Another way to create row vectors is something called linspace. So that's useful when you know a starting value, a stopping value, and you're less concerned about the spacing and more concerned about how many points. So here we would say linspace, which stands for linear spaced elements. So in this case, we started at 0. It's going to stop at 2. And in this case, it will always have those as the start and stop values. So unlike with the colon, where you might not get the stop value that you put there because of the space not hitting the actual stop value. But here we will always get those two on the ends, and it will just create the right spacing so that you'll get exactly 10 components. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 points exactly. And so we can figure out what the spacing needs to be to get 10 points. And you might think that the spacing would be 0.2, but it actually ends up being 0.222. And that's because there are 10 points, but we're dividing it into 9. There's 9 intervals. So we would take the interval length, which is 2 in this case, and divide it by 9 rather than 10. We're dividing it by the number of intervals, and that gives us the 0.22222, etc. So we've seen how to make row vectors. We might want to make column vectors, and we make column vectors. The most common way is to first make a row vector. So there's a row vector that we just made. We put some parentheses around it, and we put a transpose on it. So that little, it's the single quote symbol that is used for transpose. And so without that, we would create the row vector that we saw on the previous slides. But now, because of the transpose, we get it as a column vector. It goes down. Now, I'm showing this here for vectors, but we can apply this to matrices, and it will perform the transpose of the matrix. We just haven't yet shown how to make matrices in MATLAB, but we've seen transpose of matrices in the linear algebra part of this course, so we should know how to do that. All right, so now let's think about how to create matrices, and there are many different ways to do that. In fact, just as I said, there's many ways to create vectors, and we've only touched on a few of those, but those are the main ways. There are equally many ways to create matrices. So one way is to just fill in row by row, putting in a semicolon. Now, I didn't show this, but we could use the same idea to create a vector. So suppose we wanted a vector A is equal to, and we could just put in 1, 7, 5, 3. That would create a 1 by 4 vector that has the elements 1, 7, 5, and 3 in it. So we're taking that idea and using it here to create a matrix. I probably should have made that a capital A just to stick with our convention in the linear algebra part of the course. But you literally just fill it in row by row. So 1, 2, 3 will be on the first row. Then you put a semicolon, which tells MATLAB, okay, go to the next row. 4, 5, 6 on the second row, and 7, 8, 9 on the last row. And we have to include include the square brackets. That's part of defining either a vector or a matrix. So that's one way to do it. Now And suppose we already had defined a bunch of rows. So here we've got a command line that says x is equal to 1 colon 3 semicolon, y is equal to 4 to 6 semicolon, z is equal to 7 to 9 semicolon. And now you're seeing a new use for the semicolon. Well, we've seen two uses for it already. One is to suppress the display of a computed line that we saw earlier. One is up here to delimit the entries row by row in a matrix. And here we're seeing that we can string multiple commands on one line separated by a semicolon. So that's kind of nice. So you put a command, put a semicolon as if you're suppressing its output, put another command right after that, put another semicolon, put another command, another semicolon, and you can stack up on one command line as many as you can fit. So anyway, now after that we've got 3 different row vectors defined, and all 3 of them are the same size. That's important. And so now we can use this idea for using semicolons to define rows, and down here just put x semicolon, y semicolon, and then z, and put everything inside square brackets. And we get the same thing that we had up above. So 2 different ways to create the same matrix. We could do a similar thing with column vectors. So here's one command line that shows us creating 3 different column vectors. And these all have to be the same size if we're going to stack them side by side. And here we just put them side by side into a matrix, and without the semicolons, it's telling MATLAB, treat these as columns that are stacked next to each other. And so we get this result here. The concept of an empty matrix. We haven't talked about that in the real world of linear algebra because it's not really that important. But in MATLAB, it's common, not common, but it's often helpful to define an empty matrix. And when we get into programming and indexing, we'll see that the empty matrix can be kind of helpful. It allows you to, kind of reserve a variable that you haven't assigned anything to. But if you just put in left square bracket followed by right square bracket, it creates what's called the empty matrix. So it's like a 0 by 0 matrix. So it can play the role of an empty matrix, it can play the role of an empty column or an empty row, as we'll see when we get into later sets of notes. So for now, just file that away in your brain and think, empty matrix, interesting thing. There are some special commands for helping us make some vectors or matrices. Here we're showing them using matrices, but at least the first 4 of these can create vectors as well. And so there is this command zeros, which will create a vector or an array of all zeros. And so you just put in the dimensions that you want here. So in this case, we've got a 5 by 2. So we're doing a 5 by 2, 5 rows by 2 columns. And all the elements are 0. And likewise, the command ones, we can create ones 3 comma 3. That in and of itself will create a matrix that is, in this case, 3 by 3 and has ones everywhere. And then notice that if we do scalar multiplication, this works just like our multiplication that we learned in the linear algebra part of the course. A scalar times a matrix, the scalar just goes through and multiplies every element. So every one of the ones here gets multiplied by a 5, and so now we've got a matrix that's filled with all 5s. So that's kind of useful. The rand and rand-n are commands that allow you to create various random vectors, random matrices if you want. And I'm not really going to talk about those too much, but they work in a similar kind of way. You would put some parentheses with a number of rows and number of columns. And I should comment here for all four of these, I'm showing putting 5, 2, but I could just as easily make these vectors. So I could put 5, 1, which would give me a column vector, or I could say, for example, put 1, 5, which would give me a row vector. So a lot of possibilities there. And then this last one, I, which is kind of funny because it makes the identity matrix, which we usually use the symbol capital I for, but MATLAB chose to use the word I. You don't have to put in 2 elements here, just 1, because the identity matrix is constrained to be square, so you don't have to put them both in. So you just put in 1 number and it will make whatever number by whatever number you put in. So in this case I put in 3, it'll make a 3 by 3 identity matrix. So that's very nice. All right, once we create matrices and work with them, sometimes we need to know what their size is. So by that we mean their dimension. How many rows, how many columns. And so there is this command called size, and here I'm just running the help on size, and we can quickly see here that if we do size x and assign it to some variable d, it will return a 2-element row vector. So d will now be a row vector with 2 elements, and the first element will be m, the number of rows in the matrix X that you put in there, and the second element will be n, the number of columns in the matrix X that you put in there. And so, you know, if X happens to be a row vector, for example, then the value of m would be 1 in that case. So here they're just showing that d ends up being a vector that has first element m and second element n. And you know, we've only so far been talking about vectors and matrices. So matrices are 2-dimensional arrays. We could go to higher order arrays. We'll talk about those in a later note set. So an n-dimensional array, we could have, say, for example, a 2 by 3 by 4. We'll talk about that later, in which case we wouldn't have a 2-element vector here. We would have an n-element vector there that's telling us all the dimensions. A common way of doing this for a matrix, instead of just putting d there, we often want the elements separate, so we can literally assign it to m, n. So now, instead of assigning it to a vector, it assigns it to 2 different scalars. So if x, say, were a 3 by 2, the variable m would be assigned to the value of 3, and the variable n would have the value of 2 assigned to it. So this is a very common way to do it. I don't think I've ever done it assigning it to a vector, but I could, and then extract it from there if I wanted. A related command is called length, and so that's often more useful when we know that we have a vector rather than a matrix. So it gives the length of a vector, and so you know, regardless of whether the vector is a row vector or a column vector, it will give you the number of elements in that vector. But it's equivalent to doing size of x and then taking the maximum value of that. So if we were to do size x for a vector, it would give us a vector with a 1 and another number in it, and then the max command extracts the largest element in a vector. And so that's what this would do. So that tells you what would happen if you applied the length command to something that's not really a vector. You would get the largest of its two number of rows or columns. So keep that in mind. All right, so we already alluded to the identity matrix. Suppose we create a matrix and we would like to find the inverse of that matrix. The matrix that, when we multiply it by the given matrix, gives us the identity matrix. So there is a command, inv, and we just type help inv, and MATLAB spews out some information to us. It tells us that, oh, this is the matrix inverse. Nice. It says inv of x is the inverse of the square matrix x, so it tells us that we must put in a square matrix. If you put in something that's not a square matrix, MATLAB will return an error at the command line. That's not the only thing it will warn you about. If the x matrix that you give it is nearly singular or badly scaled. These are situations that make it difficult numerically to compute the inverse, that there are some numerical issues with the inverse. And MATLAB will give you a warning. It will give you what it thinks is the result for the inverse, but it will warn you saying, use this at your own risk. I mean, it doesn't really say that exactly. We'll see in just a minute what it says. But the warning is intending to tell you, be careful with this result. So here's an example. So you should be able to visualize without having MATLAB show you what that is. So it's the first row is 1, 1, and the second row is 1, 0. So column-wise, we've got the first column is 1, 1, and the second column is 1, 0. You should be able to calculate the inverse of this matrix by hand. It's easy enough to do that. We've seen how to do that for 2x2s. But if we use the command inverse A, we'll get this. You should also be able to verify by hand that this is the correct inverse. Now, here's an example to show you what happens if we give it a matrix that is really singular. So here we put in the first row is 1, 1, second column is 1, 2. The two rows are just integer multiples of each other, and the two columns are identical to each other. So this is definitely a singular matrix, and MATLAB gives you a warning. It says, hey, this matrix, as far as I can tell, to my working precision, this matrix is singular. And it returns a matrix that's infinity, 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 infinity. So remember, a singular matrix is sort of like a zero scalar. When you try to invert the zero scalar, you get an error, right? You cannot divide by 0. Or equivalently, you think of 1 over 0 as infinity. Well, here we get the similar kind of thing. Now, sometimes the matrix isn't really singular, but MATLAB is telling you, well, this matrix is close to being singular. So let's look at this. So remember, we introduced this variable. Well, it's a built-in variable, EPS. It already has it automatically has a number assigned to it. The number that's automatically assigned to it by MATLAB is 2 to the minus 52. That's the smallest increment between floating point numbers that MATLAB can determine. So what I've done here is I've created a matrix that looks like this. I've got the first column is 1 and 1, so that's this number and this number. Second column is going to be 1 and 1 plus epsilon. So epsilon is an extremely small number. It's the smallest, in a sense, it's the smallest number that MATLAB can keep track of. And so what I've done here is technically I've created a column vector here that is not collinear with this because it's slightly off. So if we were to look at these two vectors, there's one at 1, 1, and then I'm not even going to draw it. The second one would be ever so slightly off, a little bit higher here, right? It would come up here, not that far though. You wouldn't even be able to see it. So technically, these are two different vectors. So technically, they are linearly independent. So technically, this matrix is non-singular. But MATLAB says, whoa, this thing is close to being singular, or some other bad thing that's called badly scaled. And it's telling you the results may be inaccurate. And look at what we get here. Remember, we got infinity when we had the same vector in each of the two columns because we had two column vectors that were linearly dependent. Well, here we're getting something that is extremely large, 10 to the 15th times some numbers here. And so MATLAB is telling you, this is dicey. And then it also gives you this other thing, which is called rcond, which here is a variable, but also is a, in lowercase, is a command that you can apply to a matrix. And we haven't really talked about this, but it's a characterization of the condition of the matrix. So condition number for a matrix characterizes how close to being singular is the matrix. And so for well-conditioned matrices, so matrices that are not even close to being singular, so in other words, you might have one vector here and another one way over here. Those are not close to each other at all. For those, you'll have this rcond number will be near 1. But for things like we talked about here, where the two vectors are close to each other, the closer they get, the closer this number will be to eps. So epsilon is 2 to the minus 52. If you plug that in and see what it comes out to be in decimal, you'll see that it's really close to this number. In fact, it might actually be equal to it. So just keep your eye on that. Don't just blindly compute inverses and think that everything's hunky-dory. MATLAB will warn you, but here's a warning to you right now. If you're running a function, a program that you wrote in MATLAB, unless you go over and look at things that are spewed out in the command line window, you won't even know that MATLAB is giving you these warnings. And trust me, I see this with student written code all the time. Students will run their program not from the command line, but they'll run it, later we'll see that you can click on a run button in the editing window, and it generates some figures and they think everything's working great, but in reality, in the command window, MATLAB is very quietly, it's not making any sound, it's just spewing out these warnings, and if you're not watching for those things, you will be at risk of getting results that are untrustworthy. So let's do some arithmetic, linear algebra based arithmetic. So as I already said, if you're programming in C, to do this kind of linear algebra arithmetic, you need to write a loop to add, say for example, to add two vectors together. But MATLAB just does it. So you define your vector x, you define your vector y, and as long as they are the same size, then we can add them together. So in this case we have a 1 by 10, and in this case we have another 1 by 10. So they are the same size, and so we can add them together. And we can see that just like linear algebra addition, these just add element to element. So we have the 1 plus 1 gives us 2. Then we have our next element is, oh goodness, what do I have here? My next element would be 2 here, and it would be 3 down here. So yes, it adds to 5, and so on. And notice that we don't hit the last 20, we hit 19. So 10 plus 19 gives us 29. So it just goes element by element, just like we would expect. And subtraction would work exactly the same way. So addition and subtraction of vectors is done element-wise, just like we defined in the linear algebra part of the course. Now, multiplication is not done element by element because that's not linear algebra. When we talked about multiplication of matrices and vectors, we defined, we had a bunch of different ways of visualizing it, but they were all equivalent. So there is a rule that says how to multiply in the linear algebra context. And you can check that this is doing exactly the same thing. So here I've defined a column vector and a 2 by 4 matrix. So a 2 by 4 matrix times a 4 by 1 vector. And when I do A times X, you can verify that that is working exactly like we expect matrix times a column vector to work. Here I've defined 2 different column vectors, and then I do X transpose times Y, and you can check that this is actually a valid multiplication, right? So I have a 4 by 1 and a 4 by 1. So a 4 by 1 transpose is going to give me a 1 by 4 times a 4 by 1. So the inner dimensions match, so we can multiply. The outer dimensions are 1 by 1, so we're going to get a scalar. And so we'll get a single number. And in this case, we see that the number that we get is 0. And that's because this is actually implementing the inner product. So keep in mind, here's a simple way to use MATLAB to compute an inner product. And I just happened to pick these 2 vectors to be orthogonal to each other. And so that's why the inner product turned out to be 0. Here's another case, multiplying 2 matrices. So I've got B, which is 2 by 2, and I've got A, which is 2 by 4. So I'm going to do B times A, so that's a 2 by 2 times a 2 by 4, and we see that the inner dimensions match, so that's valid, and the outer dimensions give us the dimensions of the result, and you can check and verify that by hand that that is actually doing proper linear algebra matrix multiplication. So we've seen that all of the arithmetic that MATLAB does is doing linear algebra based arithmetic. No surprise there, because after all, it is called Matrix Lab. Now, when we talked about linear algebra, we didn't define division. And in fact, I specifically said, careful, don't put a matrix underneath a fraction sign, because that's not really allowed. So it's not proper notation in theoretical linear algebra. But MATLAB says, you know what, we can make that work for us. And so there is a way to think about division in MATLAB, but be careful. We have to make sure that it ends up being consistent with concepts of matrix inverse. So here's illustrating the idea of inverse in the context of an AX equal to B. So I've got an AX equal to B. So here's my A, 2 by 2. Here's my B, 2 by 1. And I want to solve for X. And we've already seen that if A is invertible, in which case, in this case it is, I can compute the inverse of A, which will give me a 2 by 2, times the 2 by 1 matrix or vector B will give me a 2 by 1 answer. And so that's the solution to this set of equations. So very, very easy to do that. Now MATLAB allows you to do the same thing in a little different format. So these first two lines here are exactly the same as what we did before. And then instead of doing inverse A times B, I do A left matrix divide. So notice that it's not the usual orientation for the divide symbol. So it goes from the upper left to the lower right. But that symbol is used to mean left divide. And think about it. This is really kind of what we're doing. We're computing the inverse of A and multiplying it from the left, which is different than if we did it from the right. And so we need to make a distinction between left and right matrix divide. So left matrix divide just basically solves that problem. Now, if we do it from the right, we can't put B here. If you were to put B here without the transpose and try to do B right matrix divide A, you'll get an error. MATLAB will tell you that the sizes of those are not proper for doing that. And I would encourage you to try that, see what happens. But if we do B transpose and then do right divide A, well, now we get a row vector, but that's not the solution to this AX equal to B. And in fact, you can check the numbers that we get here are not actually the same as what we got over here. I mean, aside from the fact that it's a different shape, the first solution was a 2 by 1 and this is a 1 by 2, but the values aren't the same. So what we're really doing there, that's the same as taking B transpose and multiplying it from the right by A inverse. So notice that that's why these things are called left matrix divide and right matrix divide. So just to give you a little bit more detail on these, so here's the backslash, or what's called the left matrix divide, and they tell you here that when A and B are both matrices. Now remember, vectors are special cases of matrices. So if they're allowed from a size point of view, you can put in the A position here, you can put a vector if it's the right size. But here we're talking about general A and B. So A left matrix divide B is the same as computing inverse of A and multiplying it by B. And they say, except it's computed in a different way. So the result is theoretically the same, but it's done in a computational way that makes it a little bit more robust to numerical errors. So MATLAB is very, very focused on computing things in ways that retain as much precision as possible. So in many instances, this is actually a preferred way to solve the matrix equation than explicitly computing inverse of A. So then they go on and say, if A is a n by n matrix and B is a column vector with n components so that the sizes match up, or a matrix with several such columns, then doing this left matrix divide is the solution to this set of equations. And it says, hey, if A is close to being singular, so if it's what we say ill-conditioned, it will warn you about that. If A is not square, so if it's m by n, then, and we'll get into this stuff later, we haven't really talked about this, then this left matrix divide solves a different problem, and it's called the least squares problem. And we'll talk about this problem later on in the linear algebra part of the course. Now, when A or B is a more general object, and we'll talk about those things later on in the course, you can't use the backslash. You need to use a function called ML divide. But for now, don't worry about this. I'm just putting it there for completeness. Now here is the other one. This is the one we just looked at is called backslash, and this is called slash. And for the life of me, I can never remember which one is backslash and which one is slash. And this is called right matrix divide. And here it gives you the same kinds of insight. It's saying that, you know, A right matrix divide B is the same as taking A and multiplying it times the inverse of B. Again, except it's computed in a different way, which is a little bit better from a computational point of view. And it's warning you that, you know, in some cases when A or B is what we call an object, we have to use a function call rather than the symbol. And then the last thing we're going to talk about here is matrix power. So it's the little upward arrowhead. So if we say x power y, and they're talking here where y is a scalar and x is a square matrix. So, you know, keep track of the cases here. So x is uppercase, y is lowercase is conveying to you to think about x as a matrix and y as a scalar in this case. And so we've not yet talked about how to define matrix power. We'll talk about that towards the end of the course, but I did want to introduce it here. A special case when x is a matrix and y is a scalar is when y is an integer greater than 1. And so, you know, that's like raising x to the second power, or to the third power, or to the fourth power. So for that case, it's just equivalent to multiplying the matrix times itself that many times. So I'm just giving an example here. I define a matrix A. I say A raised to the power of 2. So that's an integer greater than 1. And we get an answer. And I'm just showing that that is the same as taking A times A. Now, they do warn us here that for other values of y, so x is a matrix, y is a scalar but not an integer greater than 1, this operation is still defined, but the calculation involves things called eigenvalues and eigenvectors. And those are a super important tool that we'll learn about later, but I'm just putting it here for completeness. If we switch it around and say x is a scalar and we're raising it to the power of a matrix, we'll talk about that also later, and that also involves eigenvalues and eigenvectors. And then we could have the case where x and y are both matrices, but that doesn't work. So that will result in an error. And then again, when A or B is this more general thing called an object, we can't use the symbol. We have to use the function form m power. So hopefully that gives you some idea of how we work with matrices and vectors, how we create them using the colon or the linspace, or colon with semicolons and so forth, and then how MATLAB has built in arithmetic that is consistent with linear algebra and actually goes a little bit farther in introducing left matrix divide and right matrix divide, which is just a very simple syntax for doing some very powerful matrix computations. So we'll see you in the next set of notes.